Okay, this is the third out of four videos of the lecture that we gave on February 7th over the last lecture on section 3.3. And so here we're going to talk about a little bit more about some of the derivatives of the trig functions. You are responsible for, and I'll mention more about this in a little bit, but you are responsible for knowing the derivatives of the 6 trig functions: sine, cosine, tangent, secant, cosecant, and cotangent. Knowing what those derivatives are, you have to know those by heart, among some others. And I'll mention that at the end of the last video when I talk about test number 1 coming up. So anyway, take a look at this third page in the handout here. It talks about derivatives of trig functions. And so let's see here. This rolling right there, we go. Okay, so we've already been told that the derivative of sine is cosine, and that the derivative of cosine is negative sine. That's something that I mentioned in class the other day, and so this is not new. But with that, we want to talk about even though you've got the derivative sheet that I handed out in class, we still need to talk about how we can come up with how some of these were derived. So for example, how can we prove that the derivative of the tangent is secant squared? So on the derivative formula sheet I gave you, it just simply states the derivative of tangent is secant squared. Well, how could we prove that? One of the things that you learn in trigonometry is a lot of times when you're proving things like proving identities and stuff, that a simple technique is to replace everything with substitute in identities with sine and cosine. So in this case, tangent is sine over cosine. So we could say, well, the tangent, the derivative of the tangent of x, that derivative, that's going to be then equal to the derivative of sine of x over the cosine of x. And since we know what those derivatives are, we can use those in our proof. And so this is going to be, since this is the derivative of a quotient, we have to use the quotient rule, right? And so what that is, from the other class the other day, was how do we apply the quotient rule for a derivative? So it's going to be the derivative of the numerator. So in this case, that would be derivative of sine x. So it would be sine x prime times the denominator as it is, so times cosine x. And then subtract the numerator as it is, so sine x times the derivative of the denominator, so it'd be derivative of the cosine x, all over the denominator squared. So that would be the cosine squared of x. Okay, so the derivative of sine is cosine, so that's going to be cosine of x times cosine of x would be left there. And then I forgot to put the prime on this cosine x. We're supposed to differentiate that. So it's going to be then minus sine x times negative sine x, since that's the derivative of cosine, over the cosine squared x. And then simplify that. It's going to be cosine squared x. Now it's going to be positive because we've got a negative subtracting a negative multiple over here, so it's going to be plus sine squared x over cosine squared x. And of course, cosine squared x plus sine squared x is one of the Pythagorean identities in trigonometry, so that equals 1. So that all equals 1 over cosine squared x, and of course 1 over cosine squared x is secant squared x. All right, so there's our proof. We showed that the derivative of tangent x is secant squared x. All right, so and you should be able to do the same thing. If I ask you to prove, that the derivative of, the cotangent, actually is negative cosecant squared. You should be able to do the same thing. Change cotangent to cosine over sine, and then use the quotient property and so on. So, and you could pretty much do the same thing with all the other trig identities if you needed to. All right, so these here are just a couple of examples here of just getting some practice using the derivatives of the trig functions. So this first one here, cosecant x times cotangent x, and the derivative of that. So we're just going to straight up use the product rule, because that's the product of two functions. This cosine x, that's like our function f, and this cotangent x, that's our function g. So really we have what's the derivative of f of x times g of x. And so this is going to be equal to, well, it's the product rule says we're going to take the derivative of the first function, so cosecant x prime, times the second function as it is, cotangent x, plus then it's going to be cosecant x, right, times the derivative of the cotangent x, period. And so now we just need to, insert, take a look at your derivative sheet for now, but you're going to have it memorized. So we've got the derivative of cosecant is going to be negative cosecant cotangent. So this would be negative cosecant x cotangent x times cotangent x. So that's by taking the derivative of cosecant and putting that in there. And then plus cosecant of x times the derivative of cotangent of x. The derivative of cotangent of x is negative cosecant squared. This will be negative cosecant squared x. And then we just need to simplify this. So here we have a cotangent of x times a cotangent of x. So this would be negative cosecant x cotangent squared x. And then we'd have a negative times a positive here, which gives us a negative. And then it's cosecant x times cosecant squared x will be cosecant cubed x. And that should be it. So again, just replacing, using the formulas for the derivatives for those trig functions and applying the product rule. Now next we have another derivative we're taking, and it's the e to the x cosine x minus x squared plus 1 times sine x. Now it's important to start seeing kind of the big picture when you see some of these more complicated derivatives, and that is, what we basically have is we have two functions. I'm going to use these blocks here. Two functions multiplied together. This is like e to the x, and this is like, our cosine x. And then subtracting, then another two functions multiplied together, right? Shoot. All right, and so then so this is that block, this is that block, and then we're taking the derivative of that whole thing, right? So I'm kind of putting these blocks here to try to describe to you the big picture of what's happening. So really, we have the difference of two things, two things. And so how do we apply the sum and the difference rule for derivatives? Is that this is going to be equal to, well, these first two blocks here that are so that whatever those two things are, right? Take the derivative of that, and then subtract whatever the other two things are, and then take the derivative of that. So we're just splitting those apart here with a subtraction sign, and then we'll deal with each of the individual derivatives of those two products. So I can stop drawing blocks and start doing the things here. So this is going to be, this will be e to the x cosine x derivative of that, and then subtract x squared plus 1 times secant x. Derivative of that. All right, so the first thing here, I'm going to start not showing every little step. So e to the x times cosine x, that's a product. So we're taking the derivative of a product, so the product rule. So we're going to take the derivative of the first function, which is a derivative of e to the x is just e to the x, and then times the second function, plus the derivative of the, we'll have the first function there, and then times the derivative of cosine. Derivative of cosine is negative sine, and so we'll put a negative sign in here. Right, so that's the first couple here, and then we're going to subtract the derivative of the first, so that's x squared plus 1, so that'll just be 2x, right, and then we're going to multiply that, oops, we're going to multiply that, that 2x times secant x, and then we're going to add to that, of course, the x squared plus 1 as it is, times the derivative of secant. So we've got the derivative of secant is just going to be secant tangent x. Secant x tangent x. Okay. Put the bracket on there. So I can simplify a little bit here. So this is going to be e to the x cosine x. And then that negative will come out here, be negative e to the x sine x. And then before I take this negative through here, let's do some simplifying. This will just be 2x secant x. And now I'm going to take secant tangent x here, this secant tangent x, that's going to get multiplied into each of these terms here. So this will end up being plus x squared secant x tangent x, secant x, Lord, sorry. Let's see here, secant x tangent x, and then of course secant x tangent x times 1 is just secant x tangent x. Okay, and then this negative right here will get distributed through all that, and so this would be e to the x cosine x, subtract e to the x sine x, and then negative 2x secant x, negative x squared so negative x squared secant x tan x, and then minus secant x tan x. Okay, so that long string of terms there is going to be the derivative of the original function. Okay, so it's just getting some practice using taking derivatives here where you have different things going on. You know, in this case we had subtraction between two products. So we split it apart into two separate derivatives and then worked on each one as a product. Okay. All right, switching topics here a little bit in that we have something here called higher order derivatives. So when we've been taking derivatives, we've been just differentiating once, and so that's the first derivative. And so now we want to talk about higher order derivatives. So it says on the handout here, it says the second derivative is an example of a higher order derivative. You can define derivatives by any positive integer order. For instance, the third order derivative is the derivative of the second derivative. Higher order derivatives are denoted as the following. And so I don't know if I'm going to try to expand this a little bit so you can see it a little bit better, and then I'll shrink it back down. So we've got something here. It says the first derivative, which is all the types of derivative we've been doing, is our first derivatives. So the different notations, the prime notation could be an example here of of a prime notation would be y prime, f prime of x, and then of course the Leibniz notation dy dx, d dx of f of x, and then there's this other notation which I haven't seen that much, but this capital D with a subscript x of y. And so second derivative then would be denoted, and the notation there would be as a double prime. And then so y double prime or f double prime of x, those again mean the second derivative. And how do you take the second derivative of something? That means, well, you take the first derivative first, and then whatever function that you end up from the first derivative, you differentiate that. And so how do you use, and here it shows the Leibniz notation for the second order derivative here is d2y over dx squared. If you don't want to show the y and you're using f of x, then it would be d2 over dx squared of f of x. Third order derivative, or third derivative, would be y triple prime or f triple prime of x. The Leibniz notation d3 of y, or d cubed of y over dx cubed, or if you're not using that, using the function notation, it would be d cubed over dx cubed of f of x. Fourth order derivative, notice that after the fourth derivative, starting with the fourth derivative, you don't use the prime notation anymore. You put 4 in parenthesis. You don't just put a 4, because if you just put a 4 without parenthesis, that would mean like taking the function and raising it to the fourth power. But now that I'm telling you that if you have parenthesis around that up in the exponent, then that just simply means, in the context of taking derivatives, that's the fourth derivative, or a fourth order derivative. And so that's how you write it out. There they give you all the way out to the nth derivative, meaning, for any order of derivative, showing you some examples there. Okay, so now we get some practice here on the fourth page. So here it says, find y prime, y double prime, y triple prime, and the fourth order derivative for the following function. And the function here is 5x to the fourth minus 3x cubed plus 7x squared minus 9x plus 2. So it's a pretty simple one. It's just a polynomial. So the first order derivative is what we've been doing, right? Just take the derivative of the original function. So that's going to be, what, 20x cubed, and then minus 9x squared, and plus 14x minus 9. So that's the first order derivative. Then the second derivative, f double prime of x, is equal to, well, we're going to take the derivative of the first derivative. So here we've got the first term is 20x cubed, so the derivative of that's going to be 60x squared. Then keep going here, then it would be minus 18x plus 14. And then, so that's our second derivative. The third derivative, f triple prime of x, is going to be equal to, well, take the derivative of the second derivative. So that's going to be 120x minus 18. And then lastly, the fourth order derivative would be, I'll show here with the 4 up here. Right, so that's going to be, well, 120. Okay, so that's just a simple example of higher order derivatives. Now the question here, it says, if f of x is a polynomial of degree n, then what is the n plus 1th order derivative? Well, take a look back at the case that we just did. What degree is this polynomial? Well, it's a 4th degree. And each time we took the derivative, notice that the degree of the polynomial was decreasing. So when we took a 4th degree polynomial, when we first took the first derivative, it took it down to the 3rd degrees because we have 20x cubed. And then when we took the derivative of that, it took it down to the 2nd degree because we had 60x squared. And then when we took the third derivative, it took it down to the 1st degree, which is 120x, right? And then you can see it's going down 1 degree each time. and that was taking the fourth derivative of a fourth degree. So what would have happened if on this particular one right here, if we were to differentiate it again and do the fifth order derivative, which would be taking it to this n plus 1 because it was a fourth degree, and we would take a fourth degree polynomial and then taking it to the fifth order derivative. Well, what's the derivative of the constant 120? It's 0, right? So that's what the answer to this is going to be, is because if I have an nth degree polynomial and I'm going to differentiate it n plus 1 times, then that means I'm going to end up like this one here. I'm going to end up taking the derivative of a constant, which is always 0. So the answer here is the derivative would be 0. Okay? And last example here is an application in physics of using higher order derivatives. All right, so let me just kind of read this to you. Now, actually, there's a little typo here on the handout. You'll want to fix this and make this to the second power. It should be this should be negative 0.81 t squared. So I'm going to put the caret in there to make it be squared. Okay, so let me read the problem here. It says, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of the falling objects is s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds, as shown at the figure, down here. Their question is, what is the ratio of the Earth's gravitational force to the moon's? And I'll explain this here more fully in a second, but I want you to just understand what this function tells us, this position function, right? And we've talked about position functions before, just briefly. But the position function tells us, in this case, since we're dropping, we're talking about being on the moon and dropping a hammer and feather, and that they basically fall at the same rate of this negative 0.81, this particular rate. In this, I guess what I want to say here is that this function tells us how high off the ground is an object after so many seconds. So if you want to find out on the moon how high off the ground is this object going to be here in 1 second, you would put 1 in for t in this function. So first thing just to know, just to realize here is this s of t, this is a position function. Okay, this is a position function. And so if I plug a value in for t, that would be a time, some kind of a time, like 3 seconds, 5 seconds. I plug it into this function, and then it would tell me, the number would tell me how high off the moon's surface is the object now. And then second thing you need to know is, when I differentiate a position function, we mentioned this before, when you take the first derivative, this actually gives you a velocity function. It'll give you a function that will tell you the velocity of a particular object at any point in time. So velocity function. Now let's go ahead and differentiate that, this negative 0.81 t squared. So we're going to differentiate, so let me just kind of put it down here, negative 0.81 t squared plus 2. We're going to differentiate that, take the derivative of that. If we do that, you're going to end up with, 2 times negative 0.81 is negative 1.62, so it'll be negative 1.62. Now, and there would be a t, because it would be, this t squared would be decreased by a power. And so this function right here, this negative 1.62 t, would tell you the velocity of some falling object at any particular time t. Now, you know, and we're talking about this now because we're talking about higher order functions. So we're taking about, now we're going to just go beyond the first derivative. So now let's take the second derivative. So we're going to take the derivative of the velocity function. And so, so be s double prime of t, which means we'll just take the derivative of the second derivative. So we're going to take the derivative of negative 1.62t, which is be equal to a negative 1.62. Now, so this actually ends up being the acceleration due to gravity. So if you have a position function, the first derivative tells you a velocity function, but the second derivative tells you the acceleration. And so this is telling us, and actually the units for this would be on the moon here is negative 1.62 meters per second per second. Okay, so every second the object falls, it is increasing in velocity by 1.62 meters per second. Okay, and so this is an acceleration. Now, to figure out, they ask us what's the ratio with the Earth's gravitational force. Well, you may know from physics, the Earth's gravitational force, that's going to be negative 9.8 meters per second. Okay. All right. So if we want to find the ratio of the two, which is the question, and this would be, so if I want to do, we'll do the ratio of the Earth's gravitational force of acceleration over the moon's, because a ratio is just something over something else. It's like a fraction. So the Earth's is negative 9.8 meters per second over the moon's, which is negative 1.62 meters per second. You do that division, of course, there's we end up with the units cancel. It's a unitless answer. It's about 6. All right, and so this would mean that it's a factor of 6 higher here on the Earth, and that's why we would, you know, weigh more here on the Earth than we would on the moon. So, okay, and so that finishes up the handout. The last video I'm going to record is just going to be kind of a quick video on talking about the test coming up.